Good morning, and thank you so much. And ask the speakers to please turn off your cameras and microphones for now. And it's welcome again to the IFIN Science Innovation Showcase. It is my pleasure to moderate this first session today, and I'm also very happy to report that all of our speakers this morning are from outside of North America. So let's just dive right in. Our very first presentation is from Shahid Ali Wani from the International Center for Genetic Engineering and Biotechnology in India. And Shahid will present on the production of xylobiose and bioethanol from sugarcane dry pulp, otherwise known as bagasse. So take it away, Shahid.
Hello everyone, I am Shahid Ali from ICGB New Delhi. I'll be talking about an integrated biorefinery process for the production of highly purified xylobiose and bioethanol from the sugarcane bagasse. These are my disclosures. Before we begin, we need to understand the relationship between food, water, and energy. The water-food energy nexus is central to the sustainable development. Demand for all the three is increasing, driven by the rising global population, rapid urbanization, changing diets, and economic growth. Agriculture is the largest consumer of freshwater resources, and more than 1/4 of the energy used globally is expended on the production of food and supply. The inseparable linkage between the critical domains require a suitably integrated approach to ensure water and food security and sustainable agriculture and energy production worldwide. The global population is expected to reach close to 9 billion by 2030. And by the time the global number of undernourished people is likely to exceed 840 million. This places an unprecedented pressure on the natural resources to meet the future consumer demand. The human society is highly dependent on non-renewable energy sources as its primary source of energy. Approximately 80% of the total amount of energy used globally each year comes from the fossil fuels. But these are not going to last long, and their use is associated with the increase in the production of carbon dioxide, thus imposing a serious threat to the climate, for example, global warming. To overcome these challenges, there is a need for alternative sources of energy, which are efficient and environmental friendly. So there is a shift towards the greener approach. Though the green economy approach is being adopted to improve social well-being and to reduce environmental risks. It includes bioeconomy, bio-based economy, low-carbon economy, and circular economy. A circular economy is an industrial system that is restorative or regenerative by intention and design. It replaces the end-of-the-life concept with restoration, shifts towards the use of renewable sources of energy, eliminates the use of toxic chemicals, and aims for the elimination of waste through the superior design of materials, product systems, and business model. Nothing that is made in the circular economy becomes waste, moving away from our current linear take, make, and dispose economy. The circular economy's potential for innovation, job creation, and economic development is huge. Estimates indicate $1 trillion opportunity. Bioeconomy or bio-based economy is based on the biomass, which is central component for the sustainable economy. A large amount of agricultural waste is generated worldwide. The current availability of biomass in India is estimated at about 750 million metric tons. The farmers in India actually burn some of the waste in order to make land available for the cultivation in the next season. So Government of India came up with a policy in which these wastes are collected and used for the generation of biogas, 2G ethanol, and electricity. So what is actually there in the biomass? So before we go through what can be made from the lignocellulosic biomass, we need to understand the composition of the lignocellulosic biomass. The major component of the lignocellulosic biomass is cellulose, approximately 34 to 50%. And the second most abundant component of the lignocellulosic biomass is hemicellulose, followed by the lignin. So before these components are converted to some valuable products, it needs to be physically treated. It needs a physical and chemical treatment because of the recalcitrant nature of the biomass. So the cellulose, the main pretreatment which is used industrially is acid pretreatment, in which the cellulosic fraction is converted to glucose by the action of cellulases, and the xylose and lignin still remain in the reaction mixture, but they are unutilized and have a negative effect on the saccharification and fermentation process. So the alternative approach is to separate these components, for example, cellulose, hemicellulose, and lignin, and individually convert them to the value-added or beneficial compounds. For example, hemicellulosic fraction can be converted into xylo-oligosaccharides, for example, xylobiose, xylotriose, and xylotetrose by the action of xylonases. And similarly, cellulose can be converted to ethanol or biodiesel by yeast, for example, Saccharomyces cerevisiae, rhodotorula, or Yerovia. And also lignin can be converted to the lignin-based products. So this approach is together called as integrated biorefinery approach. So coming to the xylo-oligosaccharides, these are established prebiotics which confer human health benefits by selectively stimulating the host gut microbiota. These are used as food supplements as well as in cosmetic formulations. Due to their beneficial effects and their high market value and demand, their cost is very high. And they are naturally abundant in honey or fruits or vegetables, but due to their low abundance, the cost of the production becomes very high. So there is a need for an alternative source of this product. So it has been widely established that lignocellulosic biomass, for example, sugarcane bagasse or corn cob, they are rich in hemicellulosic component, so they can be converted into these products. So this process has two main advantages. One, that it helps in these lignocellulosic biomasses. They are abundantly available. And next, number second, this can be integrated with some other process to reduce the overall cost of the process. And how they are made. And currently the industrial approach is that acid or auto hydrolysis process. These are cheap processes, but they need specialized equipments and the high energy input is required. And some of the toxic chemicals, for example, furfural, are byproducts in the process. So that degrades the quality of the product. So the alternative approach is the greener one, which is the biological approach by enzymatic hydrolysis. So there is a low energy input, so because these enzymatic hydrolysis this occur at mild conditions, and the product is free from any toxic compound, and mostly the homogeneous mixture is formed, for example, xylobiose or xylotriose are the major products of the process. And how does these xylo-oligosaccharide work? So since these are prebiotics and they are, first of all, their one important property is that they are resistant to the acidic environment of the stomach. So they are consumed by the probiotic bacteria, for example, lactobacillus and bifidobacteria inside the intestinal lumen, and which ferment them to short-chain fatty acids, for example, acetate, propionate, or butyrate. Due to the production of short-chain fatty acids, the overall pH of the intestinal lumen is lowered. So what happens by the lowering of the pH? It creates an unfavorable environment for the pathogenic microbes, for example, E. coli and Salmonella. Its role has been also found to be in the mineral absorption as well, and it also blocks the adhesion of the pathogenic microorganisms towards the intestinal lumen. So these this whole process which occurs inside the intestinal lumen helps in the regulation of metabolic, endocrine, and immunological functions. Now coming to our work, we basically there is a requirement of a substrate as well as an enzyme for the production of this compound, xylo-oligosaccharide or xylobiose. But during this enzymatic process, we need to actually select an enzyme that can be used for the process. Fungus are known for the production of hemicellulases as well as cellulases. But before selecting any fungi, we set up a criteria that what we need from a fungus. The fungus should have been able to grow on the low-cost substrates, lignocellulosic material. It should be able to produce enzymes in the higher quantities, and endoxylenase activity of the secretome should be very high, and it should have very low beta-xylulose activity, because we don't want xylobiose or xylotriose to be converted into byproduct, for example, xylose. So, and also it should have a higher saccharification efficiency. It should be able to hydrolyze xylene efficiently, and xylo-oligosaccharide or xylobiose titers should be very high, and xylose and other sugars byproducts should be very low. So we screened around 26 isolates, and we found that group 12 isolates were good producers of xylonases, and they produce enzymes in higher titers. We also did enzyme activity assays and xylene hydrolysis profiling, and we found that this group 12 isolates, although there is not that much of higher endoxylenase activity, but we can see that the protein production is very high, and also the secretome has very low beta-xylulose activity, which is beneficial for the process. And we can also see that the xylene is efficiently converted to xylo-oligosaccharides, particularly xylobiose, and with the minimum production of xylose. So we use this multi-criteria decision-making method using a mathematical model, which is a weighted aggregated sum product assessment model, wherein we could rank the fungi on various criteria, and we found that F25 isolate was the best among the 26 isolates. So we proceeded with this in-house xylanase formulation from this F25 isolate. The next thing which was required is xylene source, which is actually required for the process. So we extracted hemicellulose from different lignocellulosic material, for example, sugarcane bagasse, wheat straw, rice straw, and corn cob. And we found that sugarcane bagasse hemicellulose was efficiently converted to xylobiose, and it can be compared with the commercial beef food xylene. And then we move forward with this hydrolysate and try to purify this xylobiose, because if we see the initial content of the xylobiose was 66% of the total hydrolysate mixture. And we used activated charcoal chromatography for the purification of this product, and we could achieve 96.29% pure xylobiose with a yield of 78% when compared with the initial xylobiose content. We also characterize this purified xylobiose by different techniques. For example, HPLC, where we can see a single peak, and there is a very little peak of xylose or other sugars, which cannot be seen here. And also, this xylobiose was confirmed to have a molecular weight of 282 Dalton by mass spectrometry. And also, the degree substitution was confirmed that this molecule, this xylobiose, is actually a dimer, and there is no other substitution. For example, arabinose residues, and there is none of them. And then we further move ahead with the in vitro utilization of this xylobiose and production of short-chain fatty acids. We used different gut bacteria, for example, Bifidobacterium species and Lactobacillus species, and we found that whether they are able to utilize this product as a sole carbon source, and we can see that two of the isolates, Bifidobacterium adolescens and Lactobacillus brevis, were able to use this xylobiose as a sole carbon source and could actually produce short chain fatty acids, which is acetate, and which was pretty good. And next, most of you will be thinking that what happened to the cellulosic fraction of the biomass. And what we tried here is we tried to integrate one more process here, because lignocellulosic biomass hydrolysate, it is difficult to go for the production at higher solid loadings. That's the reason that the cellulosic hydrolysate has a low sugar titer. And one more waste which is generated by the sugar industry is molasses. It has a very high sugar concentration that actually needs to be diluted in order to ferment efficiently to ethanol. What we did was that we tried to dilute this molasses with the sugarcane bagasse hydrolysate. The sugar concentration slightly increased from 205 gram per liter to 236 gram per liter, and it was efficiently converted to ethanol, and where we could achieve 109 gram per liter of ethanol. And there was no drastic reduction in the yield in the process. So this was also a very efficient process. And if we compare the process efficiency at different stages, because there are individual steps for the production of these xylobiose or ethanol, we can see that most of the individual processes were of good efficiency, around 68% glucan production efficiency, and then hydrolytic efficiency was 73%, and ethanol fermentation efficiency was around 91%. And similarly, xylene extraction efficiency was 73%, and xylo-oligosaccharide or xylobiose efficiency was 58%, and then purification efficiency was 78%. So the overall process efficiency was 46% from cellulose to ethanol and 31% from hemicellulose to xylobiose. So to conclude, a successful process was established for enzyme, bioethanol, and xylo-oligosaccharide, that is xylobiose production. These individual processes were integrated with greater efficiency, and there is still a scope, and this process needs to be scaled up, and the efficiency can be increased by the automation. At last, I would like to thank the Department of Biotechnology and University Grants Commission for providing me the fellowship, and ICGB, wherein I work, and Yeast Biofuel Group, of which I am part of. And I would like to thank my supervisor for guiding me throughout this work. And I would also like to thank IFINS for giving me this opportunity. Thank you so much.
Thank you so much.
Thank you so much, Shahid, for this really interesting presentation and very timely. If asked that you please rejoin now with your camera on. To have time for two quick questions. So one of the questions submitted has to do with the diversion of this pulp, the bagasse, to oligosaccharide, this is xylases versus cellulose. Is this a competition? I mean, we are very familiar with the conversion of cellulosic material into ethanol. From a production point of view and an infrastructure point of view, do you see these two processes competing, or are you able to view this as complementary?
Actually, these processes are complementary to each other. If we see that in cellulosic ethanol production process, only cellulose is converted to ethanol, and that hemicellulosic part that remains unutilized. So because that is the huge component, around 34% of the total biomass remains unutilized. So that is the strategy to convert this 34% to some valuable compound that itself has a high cost. So the overall production cost can be reduced for the ethanol production, as well as we can make some important food material that itself has a higher value.
Very good, thank you. So this is another question, maybe it touches more on the production logistics side. As you may know, in the United States, there was a big push to use cellulosic material for production of ethanol and other components, and it hasn't quite been very successful. One question that often comes to mind is, are there some potential negative effects of using this entire pulp material, harvesting it from the field as opposed to leaving some of it in the field? What are some of the unintended consequences of having such a major scale switch to the production of these two chemicals with this biomaterial?
Actually, I don't think so. There is the larger consequence if we see that for these lignocellulosic materials, just in case of India, these lignocellulosic materials, if they are not used for some important product manufacture, they are being burned down by the farmers. So that itself has environmental consequences that leads to the increase in the global carbon dioxide level. So that's why instead of burning those lignocellulosic materials in the fields, it is uh, helpful to convert them into the some valuable compound, for example, ethanol or these xylobios or xylitol in some cases.
Yeah. Yes, and very last, very quick question. Is there a push to perhaps shift the auto industry to ethanol if you can have enough production of ethanol from this material? I know this is out of your space, but for example, Brazil has made that shift.
Yeah, I think India is investing a lot in making this ethanol production process from the lignocellulosic or molasses into a successful thing, So that is why most of the bioenergy people from India are working towards this sustainable growth.
Very good. Thank you so much, Shahid. And we're now going to move straight on to our next presenter, Shema Al Atauni. Shema is with Hebrew University in Jerusalem. Shahid, if you would turn off your camera, please. And Shema will speak to us on her research on sweet and bitter molecular models and screening. Shema.
Hi, my name is Shaimal Atawane, and my talk today is about the construction of sweet and better molecular models and screening. This is one of my projects as a postdoc at the Molecular Modeling and Drug Design Lab at the Hebrew University of Jerusalem. Overconsumption of high-calorie foods and mainly beverages leads to elevated risk of metabolic disorders such as obesity, type 2 diabetes, and cardiovascular diseases. It is thus important to replace sugar in food and drinks by low-caloric sugar substitutes, called also artificial sweeteners. Only few molecules are approved as artificial sweeteners for human intake. This includes compounds of mainly three different classes: sulfonamide, polyalcohols, and peptides. No sweeteners have been found to replicate the taste of sucrose, which is used as the international standard for measuring the sweetness of chemical compounds. Current sugar substitutes are associated with unpleasant aftertastes, and some are even better. Warnings of health problems due to using sugar substitutes do not have enough supportive data. The FDA limits the daily intake of each of the approved sweeteners for a person's lifetime. Thus, new sugar substitutes are needed. In searching for a new artificial sweeteners, we need to take into consideration their solubility and stability in food and beverages, that they have no toxic effects and no aftertastes like bitter, metallic, and licorice-like, and they have no delay in sweetness onset, lingering sweet aftertaste, and sweetness adaptation. Taste sensations are mediated by taste bud cells, which are small clusters of epithelial cells located within the pharynx. On average, the human tongue has 2 to 8,000 taste buds. The sensation of different tastes like salty, sweet, sour, bitter, or umami is diverse not only within a single taste bud but also through the surface of the tongue. There is only a single sweet taste receptors which belong to the C subfamily of GPCRs and function as a heterodimer of two subunits, 2 and 3. The umami taste receptors has a closely related 3D structures of T1R1 and T1R3 heterodimers. Better receptors are numerous. There are 25 class A GPCRs recognized as better taste receptors which may function as a monomer or dimers. We use in silico methods to construct models that enable to find candidates with desired biological activity. Virtual screening may be divided into two categories, ligand-based and structure-based, depending on data on protein target. Virtual screening hits are validated by experimental tests later. No structures of the sweet receptors is currently known, and so we produce ligand-based models for sweetness. There are few known structures of beta receptors, but the large number suggests to focus on ligand-based models for bitterness also. Using machine learning algorithms, we construct classification models that can distinguish between different classes like sweet and non-sweet. To do this, we produce learning sets of known sweets versus non-sweets and of known better versus non-better molecules. Our in-house algorithm, called iterative stochastic elimination, or ISE, is used to construct classification models. Each model is a large set of filters made of ranges of physico-chemical properties that distinguish between the different classes. The best models by statistic criteria, such as area under the ROC curve, are used for virtual screening. We screen huge commercially available databases and pick first sweeteners candidates that are subsequently screened through the betterness model to pick sweet and non-better candidates. The sweet and better molecules for the learning set construction were taken from various datasets and databases and are summarized in this table, where sweet molecules are reported with sweet values. This is how my computer screen looks. We built different models for sweet and bitter tests with different datasets, including different learning and test sets, and choose the best ones for virtual screening. The AUC is a measure of the algorithm's performance, where we show the true positive rate at the y-axis versus the false positive rate at the x-axis. The ideal classification will show maximum area under the ROC curve, where correct predictions versus large false predictions are predicted correctly. False predictions are minimal in the range of 0.7 and 0.9. When the area is equal to 0.5, for example, it is considered a random and insignificant classification. Models that get less than 0.5 are considered worse models than random. Both of the sweet and better models got a high AUC which are greater than 0.9, as can be seen. The models can screen millions of molecules in a short time. A model usually consists of hundreds of filters. Each filter has 5 ranges of properties, and each molecule is tested by each filter and gets a positive number for passing the filter and a negative one for failing to pass. The final score for each molecule is normalized by the total number of filters of the model. So, we screened two available databases, the enamine database with 1.8 million molecules and the zinc database with 17 million. Our candidates are those that have high positive scores for sweetness and negative scores for bitterness. From the enamine, we found 27 candidates, and from the zinc, 187. Next step is getting these molecules and sending them for wet experiments. Here, for example, 3 new candidates which have positive scores at the sweet models and negative scores at the better models. As can be seen, the structures of the new candidates are different from those of the available sweeteners that are in use now. conclude, we have high-quality models for both sweet and bitter tests. These models were used to discover new sugar substitutes candidates which lack bitter aftertaste. The candidates have novel structures not known before to have any relevant taste. Structures are highly diverse by chemical scaffolds, different than each other and different than our learning sets. Candidates that prove to be non-toxic and soluble will be tested for binding and activating the receptors prior to in vivo studies. Thank you for your attention.
Thank you very much, Shema. Are you able to hear us? Shema was having some connectivity. So I think we will just move on to our next presentation, and then we will go back towards and have a joint Q&A after the next one. So moving on, our next presentation is by Paula Ormando. Paula is with the National Agricultural Technology Institute in Argentina, and she will speak on the health benefits of organic spelt flour produced in Argentina.
Okay, let's see. I know we've got some technical challenges going on. Hopefully folks can hear me. Let's see if we can have Shema at least by voice. Shema, can you hear? Okay. Guessing. Shema, I know was reporting that she had some challenge.
Hey everybody, this is Neil again. We may be having
So
some audio issues. Just bear with us for a second.
I am going to,
as we cue the presentation by Paula.
is that let's go ahead and play Paula's video next, okay? And then we'll circle back to ask Shema and Paula to both join us, and we will do those questions together. With that, what we're calling up Paula Ormando's presentation. Paula's going to speak to us on health benefits of spelt wholemeal flours. Paula is going to share some of the research that's been done with the government of Argentina. So with that, let's cue up Paula's video, please.
Good afternoon. My name is Paula Armando. I'm in charge of the Thermal Technology Group at Food Technology Institute in INTA. And I would like to say thank you for this space to sharing our research entitled Health Benefits of Spelled Wholemeal Flour Cultivated under Organic Agriculture in Argentina. This research is in collaboration with Leticia Mir, Francisco Di Pane, and Elena Molfese. We also like to say thank you for our organization, National Agricultural Technology Institute, for our financial support. This is our team. Here is me, Paula, Leticia, Elena, and Francisco. Well, to begin with, I would like to give an advance in a background and justification for this research. As you know, spelled wheat is an Asian grain and of course have a great potential for cultivation under organic, biodynamic, or low input farming conditions. It's an exploit and dressed grain, which is brings protection against some pathogens like Fusarium. And also, as you know, in the few years, the preference in the consumption of the food made with organic wholemeal flour, let's say it reducing the glycemic index, also increase the fiber and mineral content. Because of that, we consider that it's a good grain and also a flour to bring nutritional profile with suitable and which is suitable for bakery products. In our case in Argentina, we only have two spelled brand certificated crops and also flowers, and all the crops here in this in the fourth sub-region of my country. Here I can signal in this point. Another nice news is that in the last year, Triticum spelta was incorporated in the Argentinian Food Code, which is very good for us to investigate it and to promote the crops. So our objectives was evaluate the nutritional and rheological profile of the only two organic wholemeal spelled flours available in the market of Argentina. Here is our first spelled 1, which is named Dinkel Ecofauna, and spelled flour 2 is Overkulmer Rotkorn. They are the variety of spelled. And also we compared with, also of course, the performance with another, but it's a wheat bread flour, also wholemeal, with high quality, industrial quality. So what we do, we did indeed, we measure all these parameters, consisting in granulometry, of course, compositions, minerals, vitamins, and rheological parameters. All data was processed after statistical analysis using Infostat software, and we finally, our results were here. If we consider for the first of the path granulometry, you can see compare Dinkel against Overkulmer, you will see that in the first part of the sift, there was a major returned the flour because it's quite thick and present a lot of bran. And in the last part of the sieve, bottom is less retained. According to another nice point to be considered is the percent of protein of this first spell that we observed against this of another one with less percent of protein. For the second spell that we found is a high percent of ashes and also crude fat, and also compare with wholemeal wheat. The other values that we consider are minerals and vitamins. In this case, we analyze all these minerals and we discovered that only 3 of these were really statistical difference against the second spell. For example, sodium, phosphorus, and also magnesium presented a high value comparing with another one spelled. Finally, Riboflavin, which is vitamin 2, present differences against the other one. For the last parameters that we measured, we consider rheological parameters. As we remember that we have a high percent of protein is reflects here in the wet gluten and wetting index for Dinkel ecofauna. For the amylograph test, we measure, of course, the strength and tenacity against the stability. So as we see, the values are really, really high comparing with overcoolmer. Finally, the absorption are equal in both spelled. This is a part of the farinographic test, but in forming and stability time, we observed differences. This is the last result for the last 2 weeks. We finally performed this Mixolab test, and we found this different profile for the different 3 wholemeal flours, as we consider that these 2 spelled, finally, we suggested that we can make it suitable for making cookies and other baking products, providing, of course, carbohydrate, high protein quality, minerals, and also vitamins. This research expects to create the agri-value chain to produce and obtain spelled wholemeal flours, of course, with food safety, adaptability, and given the current concern for environment sustainability in Argentina. And finally, thank for your attention, and once more time, thank for this space for sharing our research.